We've now seen the problem of density in one or two dimensions, so now we're going to see it in three dimensions. So the way we do this is start to imagine what kind of creatures live in a three-dimensional in a three-dimensional region. Insects or things that are flying creatures generally work better. So I've done this with gnats. The G is silent, of course. We say that gnats are trapped in a cone-shaped enclosure with a layer of fruit punch on the top. We know that the gnats are certainly attracted to the fruit punch. So the density of the gnats is 1,001 plus y squared gnats per meter cubed. That's going to be our unit at a height of y above the vertex of the cone. That makes sense that there are very few gnats down here because they're not near the fruit punch, and then as we go up here there are going to be a lot more gnats because they really want to be near the fruit punch. And if we look at the dimensions of this cone, it has a height of 1 and a radius of 2. So you're going to see we're going to use a different radius than the radius of its base, but usually we describe a cone based on by the radius of its base like that. So what we want to do is we're given a density in terms of gnats per volume. Meters cubed is a volume. So what we want to do is find some unit of volume that we can add up. Now maybe you can see where we go with this. This is actually a volume of revolution. As you can see, it's if you did this by the disk method, this would simply be what curve is this? Let's point this out. This is the point 2, 1. So what we can see is that this line here is y equals 1 half x. Put it up here. So y equals 1 half x is giving the side of that cone, and that's equivalent to x equals 2y. Since we would be finding the slices here, you can imagine that what we're doing is finding disks to add up by the disk method. We're revolving using the disk method about a vertical line, so we know that we have to do this in the y direction. The disk is thick in the direction dy, and what we're interested in is what is the radius of each disk. Well, we can see that since this point here rather, is going to be 2y comma y. We can choose y independently, and we know that x equals 2y. That means that this distance here, which gives that radius, is 2y. So we can say that the area of disk is equal to pi times its radius squared. The volume of disk is equal to pi 2y squared times the thickness, that's that direction, and the population of insects in the disk is pi 2y squared dy, where this is going to be measured in meters cubed, and it's going to be multiplied by, we know gnats per meters cubed, to get the total number of gnats. That's going to be total gnats in one disk. So that's going to be times 1,001 plus y squared. So now we're just going to form the integral, write the population, in other words the number of gnats in the cone, is going to equal the integral of the population of gnats that are in one disk. So I'm going to write the same expression from down here. This is pi 2y quantity squared is 4y squared, and we're multiplying that by 1,001 plus y squared. We'll get the dy in there. And of course we're doing this, since this is in the y direction, we're doing this from the lowest possible value of the cone, in other words the 0. That's the low point of the cone up to the high point of the cone, so that's going to be from 0 to 1. And now I'm just going to simplify this and zip through the algebra. And there we go. We have approximately 6,699 gnats in that cone.